Today we are going to do an FRQ together. There is a new assignment on AP Classroom. It has 2 FRQs. The second one you will do as an assignment. The first one we're going to do together. And as pointed out on today's Canvas module, we're going to learn a new technique today. A technique that's very important, especially historically for physicists. And that's called, it sounds easy, it's called linearizing data. So you might think back in the day before computers, before even calculators, science was a little more tedious, a little more difficult to do. One of the techniques that they developed early on to make it easier to analyze data and to come to important conclusions is taking data that's not linear, like position versus time. It's parabolic, right, for uniformly accelerated motion. Well, that's obviously nonlinear. But there, I can be creative in the way I plot the data, and I can force it to be linear. And sometimes when you force a graph to be linear, the slope of that line will tell you something and allow you to come to some conclusions when you're doing some kind of lab experiment. When you're trying to, today, the problem we're going to be dealing with is an experiment used to determine the value for g, little g, at the Earth's surface, 9.8 meters per second squared. So we're going to do that. So go ahead and bring that up. Oh, and by the way, I am sorry, Matthew, I forgot to respond to you. The MCQ assignments, I'm going to unsubmit everybody's submissions if you've submitted, and you have until Sunday to finish that. I'm sorry, I forgot to change it. I was going to change it until like tonight, but then I figured I might as well give you the weekend anyway. But you'll be able to work on the second FRQ for this too. That won't be due until next week, so don't worry about that. Focus on getting the MCQ done first. I will be unsubmitting your answers right after school today, so you can get started on that again. If you're done, you're happy with it. That's fine. If you aren't done,
I looked at the results.
You can go back in and change things. All right. Okay. So for this problem, it's a long free response question, meaning on the AP exam, they expect you to spend about 25 minutes on it. Show your work for each part of the question. It's kind of like Wilbur. Wilbur over here, our conical pendulum. Remember Wilbur? Oh, he's a little askew. There we go. We got a conical pendulum, right? I think it's thrown off his balance. He's got a little bobble there. Okay. Whoa. He's been dethroned. All right. Oh, nope. Not that way. Oh, come.
Hey, look.
I'll have my editor take that out. Okay. So this is kind of like that, but look, I got a motor up here. So I can change the rotation rate of the string. Okay, I can't do that with Wilbur. It's kind of set, it's locked into the way it's designed. Essentially one speed at one radius. But in this we can vary stuff. So in the apparatus shown above, one end of a string L, string length L, entirely symbolic, no numbers for any of these things, is attached to a block of mass M, that's that guy, and the other end is connected to the axle of a motor, so that's the thing up here. There's the axle of the motor that rotates, causing the block to move in a circle of radius r at a constant speed vt. Why vt? Tangential speed. So your speed is always tangent to the circular arc that it's moving in, such that the string makes an angle theta with the vertical, not the horizontal. A student wants to use this apparatus to make measurements and create a graph that can be used to estimate the acceleration g, which we already know, but we want to determine that experimentally, due to gravity at the surface of Earth. The student can adjust the motor to achieve different tangential speeds of the block. Before I even go farther, I want to conceptualize what's going on. Right? I got a motor that I can control the speed on. And depending on the speed, it might dictate what happens, right? So what would you think? Let's say I have a certain speed on my motor, and I got a certain rotation here, certain horizontal circular motion, uniform circular motion. What happens if I turn up the speed, do you think? What would happen to M? What would it do? What's that? The radius of the circle probably increase, which means you spin this up faster, and it's probably going to go up like this, right? And then be in that circle. So not only would the radius have to increase there, but what else would also increase? If the mass went from here and then moved up to here. So it was in this circle with a larger r. What else had to increase there? Don't really know about the speed, maybe, probably. Yeah. But also, yeah, so speed, yeah, but then also the angle? Yeah, you're right, the speed would. Yeah, the speed would definitely be higher. The angle would be larger. The radius would be bigger. So a lot of stuff changes, right? So we can do additional stuff with this setup that we can't do with Wilbur. We can vary things. And that's kind of the what's a central issue in this problem. Okay. So, number AI, the dot below represents the object as it travels in a horizontal circle at a constant tangential speed at the position shown in the figure above. On the dot, draw and label the forces, not components, exerted on the object. Each force must be represented by a distinct arrow starting on and pointing away from the dot. This means draw a free body diagram. I'm going to do mine over here. What forces are acting on the mass at that location? Gravity, which points up, right?
Yep.
Points up? And I'm being silly, sorry. Gotta do something to keep myself awake. What else? Tension, where does that point?
In the direction of the string.
In the direction of the string, perfect. And it'd be about that big. And I'll call that capital T. You can call it F sub T, whatever you want. Okay, and are there any other forces? Remember, if the answer is yes, you better tell me what is the agent of that force. What's causing that force? Are there any other forces?
It's not. Is it on the ground?
It's not on the ground. Yeah, so there's no other forces. Yeah. So there's no other forces, so that's my answer. Let's see what the scoring guidelines say about that. We are going to look at the scoring guidelines for each of these. I want you to start developing an intuition as to where you should focus the majority of your energy on the actual AP exam. This problem is a pretty prime example of that. So for part AI, you get 2 points. Look, I got them both. 1 point is earned for drawing a downward force due to gravity. 1 point is earned for drawing a tension force directed along the string, upward and to the left. 2 points. Keep that in mind. I am going to go through these first parts kind of quickly because it's a later part of the problem that involves the important part of today, which is linearization. So, a double I, derive an expression for the block's centripetal acceleration AC in terms of the mass m, theta, and physical constants as appropriate. All right. Now notice, just derive an expression for the block's centripetal acceleration AC. That's what I'm looking for. This is A, I, double I. In terms of m, theta, and I like writing constants. Fundamental constants, meaning little g, big G, ideal gas constant, whatever. So I need to express this guy in terms of that. So it's kind of like this is my unknown, and I need to get an equation for it in terms of those guys. And no other variables, right? Just numbers, constants, and m and theta. Nothing else can be in there. All right. Jeez, calm down.
Sorry, I'm really bad.
So where should I go? What should I do?
Write an equation.
How am I going to write that equation?
Oh, first of all. Let's do vector decomposition.
Oh, nice.
What's that?
Let's do vector decomposition. Now, this is a case that I'd probably call to the left, the positive direction, just so I don't have to worry about a negative tension component, right? Which is fine, right? We can define whatever coordinate system we want. And then I decompose my tension vector to the horizontal component and the vertical component. Now remember, this is the angle we're given in the problem, yes? We're given the angle with the vertical.
Yeah.
This triangle is similar to the triangle that the actual cone makes with the vertical. So this is the opposite, right? This is the opposite side. So the horizontal one is actually going to be the sine component of the tension in this case. And this guy is going to be the adjacent or the cosine component. Right? All right. So with that, what equation can I write? Because I'm looking for my centripetal acceleration, which means I should probably use Newton's second law. That's what you said, right?
Yep.
Newton's second law. Good job. Newton's second law, which simply states generally that the net force on an object is equal to the mass times acceleration. Well, we're told this is horizontal uniform circular motion, so that's centripetal acceleration, which means we got a centripetal force. But remember, centripetal forces, they're only forces that actually point towards the center of the circle. And if this is the circle that the thing's moving in, the center's right here, what force is pointing towards the center of the circle? T sine theta. So this guy becomes T sine theta equals mass times centripetal acceleration. And then I see that I'm kind of onto something because I'm looking for AC, so I expect to see that in the equation, obviously. It can be in terms of m, so we're good there. It can be in terms of theta, so we're good there. What's my problem? T. Can't be there. So how do I deal with that? So think of it. We don't know any of these, but really our unknowns, in quote, A and T. So it's these guys can be there. They can be there at the end. This guy has to be there. This guy can't. So it's essentially like one equation with two unknowns. So we need what? We need a system of equations. We need another one. So what's the other equation we can get by looking at our free body diagram? T cosine theta equals what?
Mg.
Equals mg. Because we know that it's not accelerating up or down, so these forces have to balance. And the way I would do this, solve this for t, solve this like a system of equations, right? So t by itself, I solve this for t to get an expression for t, the tension. And then I could substitute mg over cosine theta in for the tension in this equation. So I could just take this guy and go, put it right there. And when I do that, I get mg over cosine theta instead of the tension times the sine of the angle equals mass times centripetal acceleration. And now not only is the t eliminated, what else do I notice happens? Everybody brought mass. Mass cancels. So we don't even need that. That happens sometimes. Don't let it throw you off. Right? Determine this in terms of these guys. If one of those guys doesn't happen to be there, that is fine. That's fine. What's not fine is having something in your answer that's not in that list. Now, if you don't have time to fix it, then leave it. You might get partial credit for it, but if you want full credit, you can't have anything that can't be a fundamental constant, a number, or whatever's in the list of variables. Okay? So, my centripetal acceleration then I've solved for. It's by itself. So that's going to be g sine theta over cosine theta. This would be an acceptable answer on the AP Physics 1 exam. But those of you in pre-cal know you can substitute what? You can that's going to be g tangent theta. So either of those would be fine. And the one that we're going to use going forward is just centripetal acceleration is g times the tangent of theta. Briefly, why is that true? If you want me to prove it to you real quick, if this is the angle theta, this is the hypotenuse, this is the opposite, this is the adjacent. If you're in algebra 2, that's fine. Let me just show you why that's true. If I have sine theta over cosine theta, that's opposite over adjacent. No, it's not. Opposite over hypotenuse, divided by cosine theta, which is adjacent over hypotenuse. Flip the guy and multiply. Opposite over hypotenuse times hypotenuse over adjacent. H's cancel. Leaves me with opposite over adjacent. Well, that's tela. That's the tangent of the angle. So anytime you see sine over cosine, it's the same as tangent. All right. All right, so there we go. That's the answer, right? It doesn't have m, it doesn't have to. But it doesn't have anything that's not in that list. So we're good to go. Let's look at the scoring guidelines for that. Look at there. Draw two arrows. Do all this stuff, vector decomposition, all that stuff, right? And watch the spread of points awarded. Oh yeah, I threw it on the ground. Number 2, or I mean, 2 points. Same amount of points for all that work as you got for the free body diagram with 2 arrows. Okay. Take home point, if you're spending 20 minutes on one part of a problem, an FRQ on the AP exam, just working algebra and it's taking a long time, you're putting a whole lot of time and a whole lot of effort into not too many points. Okay. It's not a math exam. Yes, you have to do math on it, but you're not going to get a disproportionately large amount of points for a long algebra part versus a little bit of physics part. Okay, so keep that in mind. If you're taking 15 minutes on a single part of an FRQ, you're taking too long, and you're probably going to sacrifice points in the end that you're not going to get to because you're spending too much time trying to fight for 2 points on one part. Okay. So, how is it graded? 1 point for correctly applying Newton's second law to the horizontal and vertical forces. What does that mean? The grader is looking for this, and kind of this following, and then that. The 2 equations, right? So if this was assigned to you and I'm grading it, I look for those 2 equations and I check, okay, you got that point, right? Second point is earned for combining the 2 equations to express the centrifugal accelerations in terms of the angle theta. That's either writing this or like that. So remember, they grade these fast. They glance. That's the scoring guidelines. I'm looking for those 2 equations. I see them, check. I see the answer, check. You got the 2 points. They move on to the next part. And that's how things get graded. So, and then they give an example, but yeah. All right. Now comes the important part. Number B. Use it, and this is a type of question. You will have this type of question on the AP exam. It will be one of the 5. This is the experimental design exam question. Okay? Notice that's what it's going to ask you to do. Using the experimental apparatus shown above and the available equipment, design an experimental procedure the student could use to estimate the acceleration g due to gravity at the surface of Earth. BI in the table below lists the quantities and associated symbols that would be measured in the experiment and the equipment used to measure them. Also lists the equipment that would be used to measure each quantity. You do not need to fill in every row. If you need additional rows, you may add them to the space below the table. That's a lot, right? Sound complicated? Right? You're going to have a problem like this. Let me tell you how easy they are. They sound complicated, but as long as you've done the groundwork, which we've already done, let that guide you in your experimental design question. Okay? So we're going to have to fill in these. We got to list quantity to be measured, symbol for quantity, equipment. So I'm going to copy that table real quick over here. And then I'll show you exactly how to make your experimental design question. If you've done this correctly, it's actually easy. It's actually not very difficult. Okay. So we got quantity to be measured. We got the symbol. And we got the equipment needed for the measurement. So it's like we're designing a lab that we're going to conduct by making measurements, using this equipment to make measurements of these things that we symbolize in equations. Right? All right. And this is going to lead us directly into the process of linearization. So, what you need to do when it's asked that question, like design an experiment to get started, you got to figure out what measurements you got to make, what symbols, what equations. What you do is just look at the equation that we're dealing with. This guy. I look at this guy. And then I say, all right, I'm using that equation to determine g. So what am I going to have to know in order to determine g? Look at the equation, guys. Everything's in the equation. I need to know the centrifugal acceleration. And I need to know the Angle. Can I directly measure in a high school laboratory? Can I directly measure the centripetal acceleration? If the answer is yes, I need you to tell me how.
You need the angle in the.
So that's not a direct measurement, though, right? Not the angle, but I know what you're trying to say. Yeah, that is right. We don't. We can't measure this directly. But we do know that what? The centripetal acceleration is v squared over r. All right. So if we knew v and r, can we measure r directly? Yeah, you get underneath the thing as it's spinning, and you just stand directly underneath the axis, 0, and just think, oh, it goes to there. You measure that directly, right? So we're going to have to measure r. It's the radius. In the equations, it is r. The equipment, meter stick. You literally just have to list what you have to measure in order to determine what the thing is in the equation. Right? That's how these questions go. All right. How do we measure v directly? We have to calculate it, right? We can't measure it directly, but we know that we can measure distance over time, but what distance?
From the center of the circle?
Not from the center of the circle. We're talking about the speed.
Oh. So you get to the circumference?
Circumference, which is 2 pi r, right? Divided by the special time period, capital T. All right, so to know the speed, which we need to know to find the acceleration, I need to know the radius, already in my list, and how to measure it, but I also need the period, right? So quantity to be measured, period. You could say the time needed for one revolution, whatever you need to put there. Symbols, capital T, equipment for measurement, timer, stopwatch, whatever you want to call it. There we go. What about theta, though? I need theta. How would I measure theta? You gonna take a protractor and put it up there while Wilbur's going around in a cone?
Yeah.
I would like to see you. I would like to see how you get an accurate measurement doing that.
I go with an iPhone.
You could probably do that if you're descriptive enough. Like you can take video and then, as long as you're like directly in front of it. Historically, that wouldn't have been an option. So they would say, what do I need to know in order to figure out theta here? Isn't this triangle similar to that triangle? That same angles and stuff? So that angle, the angle in my free body diagram is this angle.
The length of the string. And the radius.
I can use those to find the angle by using
Oh my gosh.
sine of theta, right? Sine of theta is r over L. So if I knew L and R, then I can find theta, right? I don't need to do it at this point anyway. I just need to know what measurements I need to take in order to determine what theta is. I just need to know the length of the string in R. Well, again, R is already up here. But then that tells me that I would also have to measure the length of the string. So the string length would be another thing we would need. And so that's L. And we just use a meter stick for that too. So, summarizing all that, I had this equation that we were told to determine in part A-double-I. And then I'm told to, okay, I want to find what G is. I want to experimentally determine G. So what measurements do I need to make in order to make that possible? Well, measurements I need to make in order to determine what theta and A sub C are. All right, well, I can't measure this directly, so what do I need to know? The speed and the radius. Radius, measure with the meter stick. Speed, can't measure directly, so what is speed? Oh, it's 2 pi r over there. I already got radius over there. I've just got to measure the period. And then, like we said, you got to measure the period. Measure the string length and the radius to use SOHCAHTOA to determine what the angle is. If we knew all those things, G is the only unknown. Look, we just did an experiment where we calculate G, right? And hopefully get close to 9.8. So that's the answer. If you look at the scoring guidelines, just those three things, right? All that stuff, all that wording there. All we had to do was look at the equation and figure out a way to determine everything else but the experimental thing that we're looking for, which is little g. And if you look at scoring guidelines, 1 point. All that junk, you get 1 point. 1 point is earned for listing relevant, appropriate quantities and equipment. So depending on the prerogative of the person, if they're feeling lenient or not, maybe they take 2. But those are the 3 things you absolutely need in order to determine G. There's no other way of doing it. Length of the string, radius of the circular path, time for the block to make 1 revolution, or the period. All right. Now, you get a lot of points for this next part. I'm not going to go into it too much because we want to get to the meaty part, the linearization. But part B says, describe the experimental procedure to estimate the acceleration g due to gravity. It's essentially describe how you would do what we just said you had to do, which is largely an exercise in your writing ability. Right? I would set the thing going. I would measure the radius by standing underneath it, blah, blah. I'd measure the string length before I even started going, so I knew that length. And I used those to figure out the angle, figure out the centrifugal acceleration. You literally just describe what you have to do mathematically. It's annoying, I know, but if you ever write an actual science paper, you gotta tell people what you did so that they can recreate it, right? So I'm not gonna go over that, but there are going to be a lot more points for that part of it. Okay, so if we look at the scoring guidelines for that part, it's 4 points. So it's the most point heavy so far. 1 point for stating a plausible method to use the apparatus to estimate G. Overall, does it make sense? You get a point. 1 point for measuring quantities that can be used to determine the tangential speed. Well, that's R and the period. Right? You talk about how you have to do that. 1 point for measuring quantities, or is earned for measuring quantities that can be used to determine theta and R. Theta, you measure R and L. 1 point is earned for attempt to reduce experimental uncertainty. That one is one I want to highlight. Always say you repeat the experiment several times. Okay. What's interesting here, and what's even more better, talking about good English skill, I got it. What's even more better is not just repeating the experiment, but varying the parameters of the experiment. G should not change, right? Even if I speed up the motor so I get a bigger angle and a bigger radius and a bigger speed, when all the relationships between all those things factor in, G should still be the same thing, right? So a better way of saying it would be repeat the experiment for different values of R, theta, and V, depending on the spin rate of the motor. That reader for that exam would be impressed. It would definitely give you that point. Okay? Maybe even extra ones, because they'd be so impressed. So when you're talking about experimental setups, always mention in some way ways to reduce experimental uncertainty. Repeating the experiment and averaging is the easiest way to do that. All right, let's get to the good stuff. How much time I got? All right. The student wants to analyze data collected from the experiment by creating a linear graph that can be used to estimate the acceleration g due to gravity at the surface of Earth. And this is a weird question, but we're going to explain what it means. State what quantity should be plotted on the horizontal axis and what quantity should be plotted on the vertical axis to produce the linear graph. Okay. What does that mean? All right. Up until this point, before physics and chemistry, what did you put on the vertical axis? Y. What did you put on the horizontal axis? X. And you come to physics, and it's like, what do you put on the vertical axis? Well, how about X on the vertical axis for position in the X direction? Put time on the horizontal axis. Put velocity on the vertical axis and put time on the horizontal. Put acceleration on the vertical, put time on the horizontal. Those are motion graphs. In our next unit, we'll do force versus displacement graphs when we're talking work and energy. In the unit after that, we'll do force versus time graphs when we're talking about impulse and changes in momentum. But you know what? You don't just have to have one thing on the vertical axis and one thing on the horizontal axis. This is where cleverness comes in. This is where scientists and physicists have to be clever. And so they realize that, oh, I can put combinations of things on the vertical axis and combinations of things on the horizontal axis when I'm dealing with a specific equation. And if I do so in such a way, I can force the resulting plot to be linear. And why would I want to do that? Because a linear graph is real easy to analyze, right? You find the slope of it, right? And the slope will tell you something in many cases. And so back in the day, before we had stuff where we could just feed stuff into a computer and have it spit out what it told us, you linearized graphs to represent complicated equations. And then you figured out what the slope told you, right? And it tells you stuff sometimes, and it's going to happen here. But before we get to that, let's dig into it a little more, because I have to plot something on the horizontal axis and on the vertical axis such that when I do it, I get a linear graph. Someone out there? Yeah, yeah.
I was just letting you know that I was in the library getting stuff set up on Chromebook. I just want to let you know that my studio class is.
Are you in my class?
I'm new.
Oh, okay.
I'm just.
Are you here now or are you still in there?
I'm still in the library. But
Okay,
I
okay.
was just gonna check in with you.
Okay.
Okay.
You coming from another school or something?
Yeah, I am.
Okay, cool.
That's what I was just saying.
Okay. So where's that? I'm sorry. So, and notice I'm just going to reference this equation again. But when it's talking about what I would graph, it's talking about like things that I can actually measure. Again, I can't actually measure this. I can't actually measure that. But what I can do is express the centrifugal acceleration as speed squared over r, right? Equals g times the tangent of theta. And then I have to realize or remember that v is 2 pi r over the period. Remember, I'm condensing it down. I'm doing what I talked about, what I would have to do, the measurements that I would have to make, and now I'm actually deriving the equation that I would put the measurement values into to determine what g was, right? So then I'm going to have v squared, so it's going to be this guy squared. And so that's going to be, when I square 2 pi r over t, I get 4 pi squared r squared over the period squared. So that's v squared. And then I still have the r in the denominator. I like writing it like that. I know it should still be in the denominator, but it's a compound fraction. It's kind of gross to think about, so I got that on the left side. And that's going to be g times the tangent of theta. Now, the answer to this question can be stated in many different ways. I prefer to group all constants, and you'll see why. You'll see why. There's a point to this, I'm telling you. Group all constants together, and I would say on the right side. And all the things that vary, you can leave them where they are. You can move them around to your heart's content. It doesn't matter. But the thing that is important, I feel like it makes this easier to understand, is just get all the constants on one side. Oh, I have a simplification, huh? Okay. So with that simplification, I have 4 pi squared r over t squared equals g tangent theta. All right. What's constant in this equation, do you think? G's constant, obviously. Pi's constant, usually. The 4 is going to be constant. No, what I mean by constant, we're going to vary things, right? We can speed up the rotation. So we expect the period to go down when we increase the rotation. We expect the radius to get bigger if we increase the rotation rate. We expect the angle to get bigger. So those things are all going to vary. What's not is g and pi and 4. Typically doesn't change. So I can get all the constants like I told you to do on one side by dividing both sides by 1 over 4 pi squared, or multiplying by 1 over that. 4 pi squared. And so when I do that, I'm going to erase my table here, but we all got that, right? When I do that, I end up with, and we're getting to the main point here, end up with r over the period squared equals g, I'm going to write it this way for a reason, g over 4 pi squared times the tangent of theta. Now remember theta we can find, I'm not going to go over it right now because question says, state what quantity should be plotted on the horizontal axis and what quantity should be plotted on the vertical axis to produce a linear graph. Again, this is where cleverness creeps in. Okay? Imagine, again, we're used to y and x. We're used to v and t for velocity versus time graph. There's nothing that says that it has to be a single thing and a single thing. There is a way to plot the quantities on this. And remember, we change, right? We start with a small rotation speed that has a certain r, a certain t, a certain theta. Then I increase the rotation speed of the motor. So I get different values for r, for the t, and for theta. And I increase it again. I get different values for the radius, the period, and the angle. And I get a range of those. And I want to plot that data. I want to make those measurements, and I want to plot it in a certain way that I get a straight line, whose slope I can analyze to find something meaningful. In this case, to find g. What would I put on the horizontal axis? What would I put on the vertical axis? Usually, students don't answer this question. And that's fine, because it's a new technique that you've probably never even contemplated before. Second period today, someone answered this question correctly.
I got an idea.
What's your idea?
On the x-axis, put period. No, never mind.
Time and radius.
What's that?
Time and radius.
Time and radius? How is that? It's deceptively simple when you see it. Remember, it doesn't have to be a single quantity. It could be a combination of quantities. It could be a combination of quantities.
I don't know which one goes in which, but r over t squared and then tangent theta over 4r squared.
Almost. And yes, that would work. That would work.
It's when we're looking
Again, there's different ways of doing this, and by the end you'll see what I'm talking about when I say that. But no, you're exactly right. What makes sense to me and why I like to group all the constants together is I like to think of this stuff is all changing, right? So that's some quantity. This right here is a constant, and this is some other quantity that changes in relation to those two. So I can call this guy, or I can think in my head, this guy's like y. The equal sign is still like an equal sign. This guy's like x. This guy's then like what? Slope. MB. Constant, right? Proportionality constant. That's a linear graph right there. So what I do is I make a column of everything I need to know, r, t, and theta. Right? So I figure out what for each trial, I get an r, I get a t, I get a theta, and then I make two more columns, and these are the ones I'm actually going to plot. Let me separate it, because these are the ones actually going to plot it. I take this r value divided by the square of that value, and I get r over t squared. And then theta, I just put that, and then I take the tangent of theta. And then this is what I plot, several data points. Remember, I turn the motor at different speeds, so I get different values of r, t, and theta. And I fill in that table, I plot those, and I get a straight line, whose slope is equal to what?
The g.
Not equal to g, not as I've done it now.
g over 4 pi.
G over 4 pi squared. So how do I determine g here? I multiply both sides by 4 pi squared. So using that, I know that the g in this case, I do this for several different iterations, right? Several different speeds, and I determine that g is 4 pi squared times whatever the value of that slope is.
I got close.
Yeah, you could plot r over t squared, right? Then put it over here. What we just did was r over t squared versus the tangent of the angle theta, right? What we could do is plot this versus the tangent of theta divided by 4 pi squared.
Then we just get g.
And then the slope would be exactly g. Yeah.
Would be
No, the slope would be pretty steep because it'd have a slope of 9.8, right? Yeah. Yes. So you could do it that way. Notice I could have t squared on this side. I could plot r versus t squared times tangent theta. So as long as you're doing this in some way that you force it to be linear, meaning you have some group of quantities that you can name A, you can let y equal that stuff, let m equal this stuff. That must be constant though, because the slope needs to be constant if it's linear. So if you put anything that varies in here, you're not going to get a linear graph. And then the other thing, that'll be your x. That'll be the other stuff that varies. Any way you want to do that. And you'll still get the same value for g. Okay. This is back in the day, they didn't have computers, like calculators even. That's an invention of the 1900s, right? How did people do physics between 1600, between Newton and the invention of electronic, assistance? Linearization was a big deal. This is stuff we can easily measure. And we just got to be clever about how we plot it. And if we're clever about that, it's all done by hand. Physics was done by hand until like the 1940s. All by hand, okay? So physics, they were doing physics by hand. This is one of the techniques that they used to do it by hand. Excuse me. Okay. So that's linearization, our first exposure to it. You're likely to see it on the AP exam, so we will have linearization problems thrown in sporadically here and there. So let's look at the scoring guidelines. How am I doing? I'm doing pretty good. So, how many points you get for all that? 2.
Oh my goodness.
2. Because all you're saying, horizontal axis, r over t squared, vertical axis, tangent theta. Right? So if you know what you're doing, obviously a lot of this time was me explaining it to you, but if you know what you're doing, you just take the same equation that we based the previous part on. We based everything off this equation, but then we just expand it out into the variables that are in our table, right? And at that point, you just say, all right, force it to be linear by grouping the constants together. Some collection of varying things equals some collection of constants times some other collection of varying things. And then you force that to be a linear graph where the slope tells you something. How do you determine what the slope is? You just look at that. But yeah, just 2 points. That part just said, what are the 2 things? Right, tell me what you plot on the vertical, tell me what you plot on the horizontal. And again, that is 1 point for listing quantities that were either measured or can be determined from the measurements. This is why you can't put centripetal acceleration, because you can't directly measure that. You have to put things you can directly measure. 1 point is earned for listing quantities that can be graphed in order to determine g. Okay. Again, it could be grouped differently, but as long as you follow the rules, you're good. First experience with that. C double I. Indicate which feature of the graph could be used to determine g. Okay, I jumped the gun here, sorry. Indicate which feature of the graph could be used to determine g. What feature of that graph could be used to determine g? The slope. Guess what the answer is?
Is it just the slope?
1 point is earned for giving an appropriate feature of the graph that can be used. The slope. Yeah.
Oh, wow, all I just said.
For a graph of tangent theta as a function of r over t squared.
So
Would
you
we
could
not,
just
would we
put
not
the
say
slope?
the slope times 4 pi squared? Or
It depends on, you want to be consistent, right? If you want your slope, you can make your slope g.
yeah,
You can make your slope g if you just put 4 pi squared under tangent theta and have this be tangent theta over 4 pi squared. Then the slope is g. So as long as you're consistent, you'll get 4 credit. It's tricky stuff, but this is especially back in the day, before modern technology, before even semi-modern technology. I mean, they were laying out the groundwork for quantum mechanics in the early 1900s, long before computers were even a thing. It's all done by hand. It's craziness. All right.
But now they have the FIQ doing linear.
That'll be due Tuesday night.
And then MCQ will be sent.
Yes.
If you already turned it in, we have to resubmit it.
I will unsubmit it. If you're happy with what you did, you can just let the time lapse and it'll automatically submit at the due date. If you want to go back in and change some things, you can change some things. All right. All right. So that's your experimental design question. That's one of the long ones on the AP exam. The FRQ section. There's 2 long ones, 3 short ones. One will be an experimental design. It will be a long one, meaning you're expected to take about 25 minutes on it. Yeah. Linearization. Good stuff, right? Good times. Smack the like button and stuff.